All right, we're dealing with Chapter 10, Section 2 on exponential functions, which is Learning Plan 5.8. We're going to define and graph these functions, solve exponential locations, and then do some applications. Remember, an exponential function is a number to the x power. A has to be greater than 0, and A will not be 1, otherwise it would just be 1 all the time. All right, it will get close to but not touch the x-axis. So let's look at this first one. -2, 10 to the negative second is 1/100th. 10 to the negative first is 1/10. 10 to any number to the 0th power is 1. 10 to the first is 10. 10 to the second is 100. So back 2, up 1/100th. Back 1, up 1/10. 0, 1, 1 is 10. So it's going to go like this. You try this one. All right, so 4 to the negative second is 1/16th, 1/4, 1, 4, and 16. So back 2, up a 16th, back 1, up a 4th, 0, 1, 1, 4, 2, 16. So it's going to come in like this. This one, back 2 is 1/9, back 1 is 1/3, 0 is 1, 1 is 3, and 2 is 9. So back 2, up a 9th, back 1, up a 3rd, 0 is 1, 1 is 3, and 2 is 9. Okay, so what do you do if you have a number that's between 0 and 1? Well, 1/4 to the negative 1/2 is 16. 1/4 to the negative 1 is 4. Any number to the 0th power is 1. 1/4 to the first is 1/4. 1/4 to the second is 1/16th. So back 2, up 16, back 1, up 4. 0 is 1. 1 is a 4th, 2 is a 16th, and so on. So it's going to be like this. You graph this one. -2 is 100. -1 is 10. 1, 1/10, 1, 100th. Back 2, up 100. Back 1, up 10. 0 is 1. 1 is a 10th. 2 is a 100th. So it's going to be like, like this. So if it will always contain the point 0, 0, 0, 1, it will always rise if A is greater than 1. It will always fall if A is between 0 and 1. Okay, it'll approach but never touch, and we call that an asymptote. The domain will be all the numbers, and the range will be from 0 to infinity. Let's try this one. A little bit more complicated. First thing we have to do is figure out what 4x minus 3 is. 4 times 0 is 4, is 0, minus 3 is -3. 4 times 3/4 is 3. 3 minus 3 is 0. 4 times 1 is 4, minus 3 is 1. 4 times -1 is -4, minus 3 more is -7. 2 to the negative third is 1/8. 2 to the 0th is 1. 2 to the first is 2. 2 to the negative 7th is 1/2 to the 7th. So we get positive 7th, that is. So over 0, up 1/8. Over 3/4, up 1. Over 1, up 2, back 1, up, whatever that'd be, 1/64th. And so our graph is going to go like this, kind of. Okay, you do this one. All right, so we have 2x minus 1, and then 4 to the 2x minus 1. 2 times 0 is 0, minus 1 is negative 1. 4 to the negative first is 1/4. 1/2, 2 times 1/2 is 1, minus 1 is 0. Any number to the 0th power is 1. 2 times 1 is 2, minus 1 is 1. 4 to the first is 4. 2 times negative 1 is negative 2, minus 1 more is negative 3. 4 to the negative third is 1/64. So over 0, up 1/4, over a half, up 1, over 1, up 4, back 1, up 1/64. So our graph is going to come in like that. All right, next one. We see some equations. We're supposed to figure out how to solve them. An exponential equation is this equation that has a variable and an exponent, such as 9 to the x is 27. If a is greater than 0 and a does not equal 1, then a to the x is a to the y, and a to the x is a to the y, then x equals y. So the way to do this is each side must have the same base. If the two sides of the equation do not have the same base, we have to make sure that they get the same base. Simplify the exponents, and then set the exponents equal using the property given in this section and solve the equation. So let's look at this one. 25 to the x is 125. So the way we go about solving this one is we have to make sure we get both sides having the same base. 25 to the x is 125 is 25 to the, well, if you write 125 is 5 to the third, which is 25 to the 3 halves. The other way to do this is to write both of them with the base 5. This is 5 squared to the x. This is 5 to the third. That might be the easiest way to do this. This would be 5 to the 2x equals 5 to the third. 2x equals 3. Once we get the bases the same, then the powers are the same. X equals 3 halves. Next one. This is 2 to the third x. This is 2 to the fourth. 2 to the 3x equals 2 to the fourth. 3x equals 4. When the bases are the same, the powers can be compared. X equals 4 thirds. Now, in this case, we have a little bit tougher problem. 5 squared to the x minus 2 equals 5 to the third to the x. This is 5 to the 2x minus 4, because you multiply this by each part, equals 5 to the 3x. Now the bases are the same, so the exponents can be compared. 2x minus 4 equals 3x. Subtract 2x from both sides. You get x equals negative 4. Another example. This is 2 to the second to the x. This is 2 to the negative fifth. So we have 2 to the 2x equals 2 to the negative fifth, 2x equals negative 5, x equals negative 5 halves. Now, sometimes we have situations like this. 3/4 to the x is 3 over 2 squared to the x. That is 9/16 to the negative 1, which is 3 squared over 2 to the 4th to the negative 1. 3 over 2 squared to the x. Now we have to take all the powers out, so we have 3 to the x over 2 to the 2x equals 3 to the negative second over 2 to the negative fourth. That one's not going to be easy to solve, is it? So we have x equals negative 2. Yeah, I guess that would be true. This is 3 over 2 to the second, and this would be 3 over 2 to the second to the negative 2. So x is negative 2. You do these three. First one, you have 3 to the 2x minus 1 equals 3 to the third, to the x plus 4. So 3 to the 2x minus 1 equals 3 to the 3x plus 12. You take the 3 times both of those parts, and you get 2x minus 1 equals 3x plus 12. Subtract 2x from both sides, subtract 12 from both sides, and you get x equals negative 13. I'm going to switch colors for the next one. 5 to the x equals 5 to the negative fourth. So x equals negative 4. 2/7 to the x equals 8 over 343 to the negative 1. 2/7 equals 2 to the third over 3 to the third, no, not 3, 7 to the third, excuse me, to the negative 1, which is 2/7 equals 2/7 to the third to the negative 1. This is x, by the way. So we get 2/7 to the x equals 2/7 to the negative third. X equals negative 3. What do you do with exponential growth and decay type problems? Well, here's an example that shows the carbon dioxide concentration in the air, which appears to be a exponential function. The function is defined by f of x is 266 times 1.001 to the x, where x is the number of years since 1750. We're supposed to find the concentration in 2007 So let's see what we get. So we would take, how many years has it been since 1750? So we would take 2007 minus 1750. And we get 257. So this is to the 257th. So we would press 266 times 1.001 to the 257, and we get 343.9, which is pretty close to 381. Now we're supposed to find out what it would be in 2000. Well, we still have 1750, so 2000 minus 1750 is 250 years. We have to get the formula here. 266 times 1.001 to the x. So we would press 266 times 1.001 to the 250, and we get 342 parts per million. Okay. Another one. The atmospheric pressure at a given altitude in meters can be approximated by the function f of x is 1038 times 1.000134 to the negative x. What was the concentration at ground level? So we would take 1038 times 1.000134 to the 0th. Well, any number to the 0th is 1. So this is 1. So at ground level, the pressure should be 1,038 millibars. At 5,000 meters, 1038 parentheses 1.00134 to the negative 5,000. So 1038 times 1.00134 to the negative 5,000, and it comes up with 1.28 millibars, which is not very much pressure. In fact, at 5,000 meters, there is very little pressure compared to at ground level. Okay, how about what would it be at 6,000 meters? Well, that would be 1038 times 1.00134 to the negative 6,000. 1038 times 1.00134 to the negative, 6,000 is 464.6 millibars. You know what? I think I made a mistake on the last one. I don't think I had enough zero in the problem when I did it. I should have had one more zero in here. Let's try it again. 1038 times 1.00134 to the negative 5,000 equals 531. I was going to say that did seem a little small. The other reason that I knew I was wrong is when I tried 6,000, I came up with more. So there wouldn't have been that few of millibars at that high an altitude.